The thermodynamic property, entropy, is given in differential form as ds equals dq divided by T for a reversible process, where dq is the differential heat transferred to a system, and T is the temperature at which this heat transfer occurs. To calculate the change in entropy of a system during a process, we integrate both sides. So S2 minus S1, the change in entropy, is equal to the integral of dq divided by T from state 1 to state 2. Entropy is an extensive property of a system, and it is measured in kilojoules per Kelvin. The specific entropy is an intensive property and has the unit kilojoules per kg per Kelvin. The entropy change of a system during an internally reversible isothermal heat transfer can be determined by performing the integration. Since the process is isothermal, T is constant, and we can bring it out of the integral. And this becomes S2 minus S1 equals Q12 divided by T. And this is the entropy change for a reversible isothermal process. A piston cylinder device contains a liquid vapor mixture of water at 300 Kelvin. During a constant pressure process, 750 kilojoules of heat is transferred to the water. As a result, part of the liquid in the cylinder vaporizes. Determine the entropy change of the water during this process. What we have here is a saturated liquid vapor mixture at a saturation temperature of 300 Kelvin. For every pressure, there is a corresponding saturation temperature. So, as long as our pressure remains constant, the saturation temperature will remain 300 Kelvin. And we're told the process is a constant pressure process. This means the process is also isothermal, since all the heat added only goes to converting more of the liquid to vapor. And for an isothermal process, the change in entropy is given as Q divided by T. So the change in entropy is equal to 750 divided by 300. And this gives us 2.5 kilojoules per kg. A process during which the entropy remains constant is called an isentropic process. A reversible adiabatic process is an isentropic process since dq equals 0. And if ds equals dq divided by T, then ds equals 0 for an adiabatic process which is reversible. We have used PV diagrams a lot in this series. In second law analysis, it is very helpful to plot the processes or diagrams for which one of the coordinates is entropy. The TS diagram is one which is commonly used. So we can arrange the defining equation of entropy, ds equals dq divided by T, as dq equals Tds. From this, we can tell that dq corresponds to a differential area of the TS diagram. The total heat transfer during a process is obtained by integration. And so the integral Tds from state 1 to state 2 corresponds to the area under the TS diagram for the process. We can therefore conclude that the area under the process curve on a TS diagram represents the heat transfer during a reversible process. This is similar to how boundary work is represented by the area under the process curve on a PV diagram. We can represent a Carnot cycle, for example, on a TS diagram. Remember, a Carnot cycle consists of a reversible isothermal expansion, a reversible adiabatic expansion, a reversible isothermal compression, and a reversible adiabatic compression. The isothermal expansion is represented by a horizontal line on the diagram. During this process, an amount of heat, QH, is absorbed from the high temperature reservoir, TH. The adiabatic expansion, which follows, is a reversible one, and so it is isentropic. We represent this using a vertical line on the diagram. Next is the reversible isothermal compression, which we represent as a horizontal line. During this process, a quantity of heat, QL, is rejected to the low temperature reservoir at temperature TL. Finally, we have the reversible adiabatic compression, which is also isentropic. The shaded region represents the net work transferred to the system during the cycle, QH minus QL, which is equal to the net work output from the system. Recall that for a reversible process, dq equals TdS. We can use this in the equations we already know to find the entropy change for a process. The differential form of our energy equation for a control mass is dq minus dw equals du. Differential boundary work, dw, is equal to pdv. So substituting dw equals pdv and dq equals tds, we have tds minus pdv equals du, or tds equals du plus pdv. Also, recall the differential form of enthalpy. dH equals du plus pdv plus vdp. So dH minus vdp equals du plus pdv. And so we can write TdS equals dH minus vdp. Both of these equations are very useful since they relate entropy changes of a system to the changes in other properties. We can use our TdS equations to obtain expressions for the entropy change of an ideal gas. Using TdS equals du plus pdv, we can rewrite this as ds equals du divided by t plus p over t dv. For an ideal gas, du equals Cv, the specific heat at constant volume, multiplied by dt, and the ideal gas equation Pv equals RT, which we can rewrite as P divided by T equals R divided by V. So ds equals Cv dt over T plus R dV over V. Integrating both sides, we have this. For ideal gases, we make the assumption that the specific heat at constant volume is a constant value, and so we get S2 minus S1 equals Cv times the natural logarithm of T2 divided by T1 plus R times the natural logarithm of V2 divided by V1. Repeating the same process for TdS equals dH minus VdP, we have ds equals dH divided by T minus V divided by T times dP, and dH equals Cp, the specific heat at constant pressure, multiplied by dt. And from Pv equals RT, we can write V divided by T equals R divided by P. So ds equals Cp dt over T minus R dP over P. Again, we make the assumption that the specific heat at constant pressure is a constant value. So taking the integral of both sides, we have S2 minus S1 equals Cp times the natural logarithm of T2 divided by T1 minus R times the natural logarithm of P2 divided by P1. Air is compressed from an initial state of 100 kilopascals and 17 degrees Celsius to a final state of 600 kilopascals and 57 degrees Celsius. Determine the entropy change of air during this compression process by using specific heats. Cp equals 1.005 kilojoules per kg Kelvin and Cv equals 0.718 kilojoules per kg Kelvin. For the inlet conditions, we have the inlet pressure as 100 kilopascals and inlet temperature as 17 degrees Celsius or 290 Kelvin. For the final conditions, we have the final pressure P2 as 600 kilopascals and the final temperature T2 as 57 degrees Celsius or 330 Kelvin. We can determine the change in entropy using ds equals Cp times the natural logarithm of T2 divided by T1 minus R times the natural logarithm of P2 divided by P1. We can get R from Cp equals Cv plus R. So R equals 1.005 minus 0.718, which gives us 0.287 kilojoules per kg Kelvin. So substituting all our values to find ds, we obtain the change in entropy as minus 0.3844 kilojoules per kg Kelvin.